Hello, 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 and welcome back to Kerbal Space Programming. Kevin here, and today we are going back into space. No more hover scripts for us. We'll definitely be returning back to our hover script tests, but in the meantime, we have some contracts that indicate that there are some Kerbals who are stranded in orbit. So we are sending up a brand new vessel, having unlocked struts and launch clamps and various other things. We're running this on solid rocket boosters, and we've also affixed a launch abort system that we have been contracted to test that we will discard in the early stages of the flight. But it's been too long since we've gone to space, so it's about time for us to do that. And we see that we're going mostly up, and there's our first stage burnout. The solid rocket boosters doing their stuff, and we're just waiting until we reach the correct altitude to complete our contract. Let me just scroll down. There we go. And there we go. Ditched the top and the solid rocket boosters, and we got some science and we got some fun for testing the launch escape system. And one of the reasons that we are going up at such a crazy altitude is, or at such a crazy direction, I should say, is because this is very non-aerodynamic once we have lost our launch abort system, because that was kind of serving as our nose cone on the top of this. But yes, we are running with a much taller rocket, and this is kind of a test to see whether this new launch vehicle will work as a system for getting greater and bigger payloads into space. But that being said, our primary mission for today will be to rendezvous with some stranded Kerbals in orbit. And we've outfitted our main, or our upper stage of this rocket with some empty crew modules in which they can take refuge, and we can return them back to the planet Kerbal, which should also mean that they can join our astronaut corps. And there we see we are up, getting very, very close to space, and we will begin our circularization using the remainder of the main stage, and then finally with the a little bit of the fuel of our upper stage. Now, for those who have played Kerbal Space Program, you will know that rendezvousing in orbit is one of the more challenging tasks, that it is actually easier to hit a planet than to hit another vessel. And there we go, we are circularizing. But, and you will notice it is equally challenging in KOS, so we will have to take some time to describe our technique. And now we can take a look as we have finished our circularization. There we go, ready to rescue Kerbals. So let's take a look at our launch script, and there's honestly not much new. I just want to go over one quick function that we created real quick. I called this function burnout, because you remember in the past we've done things like set prev thrust to max thrust, and then wait until prev thrust minus max thrust is greater than 10, and then stage. And this is basically just a way for us to say what is the maximum amount of thrust that the rocket can provide, and then we'll go ahead and wait until the maximum thrust that it can provide drops significantly, and then we'll go, oh, we must have had an engine burnout, so let's go ahead and stage. And sometimes with stage, sometimes we go, okay, I know that there's a burnout, I wanted to know about that, but I don't want to automatically stage. Well, I wrote a function that's going to kind of handle both of these cases for it, and I've called it burnout. So first we're going to set a variable called burnout check, and we're going to set it to reset. Now we're going to declare our function, and we're going to say that it takes one parameter. Remember, when you have a parameter, it means you can call things inside these parentheses, and we'll say true, or we could say, burnout false. Now, okay, so the first thing this is going to do is it's going to say, is burnout check equal to reset? If it is, then first off, we're going to return false, because we're going to say we didn't have any previous thrust to compare this with, so we're going to assume that you didn't burn out. Then we're going to set, well, not then. Before that, we're going to set burnout check to the max thrust. So then the next time that we call this function, we have that burnout check so we can compare it when we are running our function. So because we're returning inside here, it means that none of the rest of this code will be executed the first time that we call this function, because we immediately return. This return function, or this return statement, jumps us out of the function right away as soon as it reaches that point. But because we're setting burnout check to max thrust, that means the next time that we run, well, this if condition is going to return, it's going to evaluate to false. So we won't run any of the stuff in here. We'll just jump down to the next check. So the next check we're going to do is the same thing that we had written ourselves. We'll say if burnout check minus max thrust is greater than 10. So we had a significant decrease in our available thrust. And now we have to figure out what to do because there was a burnout event. We're going to say if auto stage, remember that was the thing that we passed in, being true or false. Well, if we're supposed to auto stage, then we'll set our current throttle to whatever the throttle was. There we go. Let's pretend that I have that in there. Yes, we'll set our current throttle to whatever the throttle is right now. Then we'll lock the throttle to 0. That's kind of important because we don't want to be, okay, we'll pretend I had that in there from the get-go. And we'll wait a second. So we're throttling down. We're going to wait a second, then we'll stage, and then we'll wait another second. And then we will lock our throttle back to what the throttle was before we throttled it down. And that's only if the argument passed in told us to auto stage. Next, we're going to set burnout check to reset because now we don't know what our new max throttle should be. So we're going to say, next time you call me, I'm going to start all over. And I'm going to go ahead and return true. So say, yep, there was a burnout event. And then finally, if none of those things happen, we'll say return false. We didn't detect a burnout event. So that's just a helpful function that we'll be able to use kind of throughout the rest of our launch. So let's get into the actual launch stuff, and I've kind of broken this down into little chunks. Now, we did have kind of a gravity turn library that we had written up. We're not going to use that here because the solid rocket boosters have a very high thrust, and if we try and turn over in the lower atmosphere, we can get very unstable really quickly. So what we're going to do, and this is less efficient than it could be, but we're going to go kind of straight up for quite some time, and then we'll do our gravity turn much later. So the first thing, we're going to lock our throttle to 0 because we don't want our main engine firing. We're just going to rely on those boosters. We're going to lock our steering to up, and then we're going to stage. Next, we're going to wait until the boosters burn out. We're passing in false. We say, don't go ahead and auto stage because we have this escape system that we have a contract to test, and it has a bunch of conditions that need to be met. We need to be above a certain altitude and below a certain altitude. We have to have a vertical speed above 200 and less than 500. So in addition to waiting for these to burn out, we also want to wait until those conditions are met before we stage. So we'll do that, and then we go, okay, those conditions were met, we'll stage. We'll wait 2 seconds and then throttle up. And now we'll lock our steering to east at 45 degrees off the horizon. So that means that we're going to be kind of splitting the difference between up and to the east. So once we get our apoapsis fairly high, remember 70,000 is the top of the atmosphere, but once we're getting close to there, we're going to turn over even further, just 10 degrees off the horizon. And then once our apoapsis is 80,000, then we'll go ahead and say, okay, we're just going to coast until we get there. So we lock the throttles to 0. Then we'll wait until we are close to our apoapsis, the ETA apoapsis. We'll lock our steering to exactly along the horizon, so 0 degrees, and we'll lock the throttle to 1. And now we're going to use that burnout function again. We'll say until our periapsis, remember the lowest part of our orbit is greater than 70,000, which is the top of the atmosphere. Then we'll say burnout true. And we're not actually using this value. We're just saying if you burn out, please auto stage because we're passing that true value. And then we'll just wait a second. So this is the actual check that'll bust us out of the loop when our periapsis is there. But meanwhile, while we're waiting for that to happen, please go ahead and auto stage for us. And then once we're done with that, we'll lock the throttle to 0. And the last thing we're going to do is enable our antenna. So this is how we got ourselves to orbit. Now let's talk about how to rendezvous with the other Kerbals stranded in space. So it's back to trusty Photoshop to explain how we are going to rendezvous with these stranded Kerbals. So we are in a relatively low orbit, and it's a fairly similar orbit to these stranded Kerbals. But there is a problem, and that is that we're kind of distant. And because of the gravity of the big planet that happens to be beneath us, if we try and say, okay, well, if we thrust forward, that doesn't actually work because gravity still pulls on us. So all that we end up doing is increasing the size of our orbit. And if we were to try and thrust backwards, well, we would fall into the planet, and that's not good. So instead, what we're going to do is try and figure out how to change our orbit such that these two crafts, or I guess space occupants, will meet each other. So let's imagine that this Kerbal's orbit is 3,600 seconds. It's not, but we can use our imaginations. We'll trust ourselves that much, right? But we've got an issue in that there is a lag between where we are and where this Kerbal is. So what we would like to be able to do is to boost ourselves up into a higher orbit, because then it will take longer for us to complete a revolution, because this 3,600 second orbital period means that after 3,600 seconds, it will be exactly in the same place that it started. So what we want to do is we want to make sure that we end up taking even longer to get around to the same point. And we're going to do everything at our own periapsis. That way we don't have to worry about accidentally thrusting in such a way that we end up getting into the atmosphere. So we're going to boost ourselves up into a higher orbit because this is going to take us longer. We're covering more distance. So this thing will go ahead and, it'll complete its revolution. By the time it completes its revolution, we won't be quite there yet. But what will hopefully happen is that we'll meet up somewhere around here because we've boosted our orbit. We've lagged, we've added this amount of delay. And now these two things are together and they can go off flying and attacking all kinds of cool stuff, right? So how do we figure out what this orbital period should be for this higher orbit? Because we want to delay ourselves roughly this segment much, but we want to figure out, well, how much time does that mean? We want to figure out what is the total time of this higher orbit. So, well, we can start off by saying, well, it should be at least 3,600 seconds plus whatever this is. So we'll say 3,600 seconds times 1 plus whatever percentage of the orbit that is, right? Because, this whole thing is 3,600 seconds. Well, then this thing is some percentage of that. So we can actually figure this out because we, in previous episodes, we wrote an orbit script that will take the longitude of a target and ourselves and get the angular difference. And this will give us a certain degree. So we can actually look and say, okay, well, what are the degrees here? And we know, okay, that's maybe 45 degrees. So that's, what is it? An eighth of the orbit, right? So we can go ahead and say, okay, well, that's great. We'll just make sure that we're 3,600 plus 1/8 of 3,600. So we can revise our formula and say, okay, we'll say this new orbit that we want to put ourselves in to make sure that we encounter this Kerbal, so that make sure that it has time to get to here by the next time round, should be 30, whatever the period of the target is, times 1 plus this degree divided by 360. We've got 360 degrees in a circle, so we're going to figure out, well, this degree is some percentage of the circle. So, 45 divided by 360 will get us that percentage. So that's what we're going to do. We're going to get ourselves a rendezvous. So now that we have sufficiently photoshopped, it's time to take a look at our rendezvous script. So the first thing that we're going to do is we're going to download our orbit KS file. And we wrote this in a previous episode, and it's got just a couple of helper functions. We're also going to download a file called rescuer.functions.ks. And this is going to handle some of the more complex logic that we're going to have to worry about. And this is a common strategy in programming, where instead of saying, stage and then wait and then stage and, whatever, you just go ahead and write a functions that you'd say, function, do something complicated. There we go. And instead of actually writing out all of these steps, you make your program and you structure it in terms of function calls. You'd say, perform ascent and then circularize and then, go to the moon. And this way, when you're reading your script, you can easily kind of look at these steps and get an understanding of what your program is supposed to do, even though the details of exactly how these things happen are a little bit hidden from you. So we're going to go ahead and hide some of that complexity inside this rescuer functions.ks. And we're going to go ahead and run both of those so that the functions that we write in there are going to be available. One of the functions that I've thrown into rescuer functions is notify, which you may remember from previous episodes, to display some text to the screen. So the first thing we're going to do is we're going to set our victim to Sigkin's Hulk, and this is the body that Sigkin Kerman is currently in, and that's what we're going to end up targeting. We're going to set our target to orbitable victim, and that's a function that we get in our orbit script, and it's just a way for us to set what our current target is. And we'll notify that we're going to begin our rendezvous procedure. So the first step is that we want to make sure that we are close to our periapsis before we start doing anything, because if we mess around with our orbits too much when we're at the lowest part of our orbit, we risk ending up in the atmosphere, and that can throw things all kinds of crazy. So what we want to do is we want to figure out our target angle, and we wrote a script to do that previously that's going to give us the angle that a particular thing is ahead of us. And we're going to pass in victim here, so we're going to say how far ahead of us is Sigkin's Hulk. Then we're going to say, okay, well, based on that, we want our target orbital period, the time that it takes for us to do a complete revolution, to be, and this is from our Photoshop stuff, the target's current period times 1, plus then that target angle divided by 360. Now there's a small tweak here that we've made from Photoshop, and that is that target angle gives us a value from 0 to 360 that represents how far ahead of us this thing is, and we want to know the angle that it is behind us because we're slowing our orbit to let it catch up. So if the thing is 90 degrees behind us, then target angle is going to end up being 270, and we want the value to be 90. So instead of saying target angle divided by 360, we'll say 360 minus the target angle to get the degrees that it is behind us. We'll divide by 360. So this is going to be 1 plus, so we'll end up with something like 1.06 or something like that. Okay, well, 1.25 or something like that. So we want to make sure that our desired period is the target's period, but a little bit more so that it has time to catch up with us. So we've got that value now, and we'll say we're going to boost our orbit. We'll say we want to change our period to the desired period. We're not going to say how, we just want to make sure that that happens, and that'll be something that we'll write in our functions.ks file. We'll wait again until we get to periapsis, because that means that we've done a full revolution around the planet. And that means that by that point, we should be pretty darn close to the target. Now, the next thing that we want to do is slowly get ourselves closer and closer until we are within 1,000 meters of the target. And at that point, we can go ahead and have Sigkin hop out and make his way over to our rescue craft. And this is where writing things in functions really helps. We'll say we'll await the closest approach. So we'll wait until we are the nearest that we're going to get to our target. Then we'll cancel the relative velocity. So it's going at a certain speed, we're going at a certain speed. We want to make sure that we are as close as possible to, we want to make sure that those, mostly match. And then we'll go ahead and say approach. So we want to fire in the direction of the target. And then we'll wait until we're closest, and then we'll cancel, and then we'll approach, and we'll keep doing this until our distance is less than 1,000. And then finally, once we've done that, we'll be out of the loop. We'll say cancel any remaining velocity difference between us, and then we'll notify that we are done. Okay, so let's really quickly talk about the functions that we have to write to make this thing work. So first off, we have this notify function, which we wrote in a previous episode, and this is just going to call something that we get from KOS called HUD text, which is just going to go ahead and display this message in nice big and white letters for us. Next, we've got this whole await closest approach function. Well, how do we figure out if we are getting close to the thing? Well, we'll say until false, and this is a loop that will run forever. We'll say, okay, set the last distance to the target's distance. So maybe it's 500 meters away, right? Then we'll wait a second and we'll check the distance again. We'll say if the distance is greater than the last distance, well, then that means we're moving away from it. Maybe the new distance is 505. Well, that's not good. That means that we are moving away, and therefore we have hit our closest approach. So go ahead and break. So cancel this loop, and then we can go ahead and continue. So we've written our await closest approach function. Next, we need a function to cancel our relative velocity. So we're going to have to lock the steering to our target velocity orbit to the minus the ship velocity orbit. And this is a little bit complex. So when you're playing Kerbal Space Program, you can actually set your nav ball to operate in target mode, and then you get a prograde and a retrograde vector that are based on your relative velocity to the target. We don't actually have that available in KOS, so we have to calculate it ourselves. Now, what we do get from KOS is that when we call this velocity orbit, is we get a vector. And we'll talk a lot more about vectors in future episodes, but this is something that we get that's, an X value and a Y value and a Z value. So it's basically a direction in 3 dimensions. And what we're going to say is, well, we want to lock our steering to the difference between the target's direction and our direction. And then we'll go ahead and wait 5 seconds to make sure that the steering can go ahead and do that. So by taking the difference, this ends up pointing us at what would be the quote-unquote retrograde vector if we were in target mode. We'll lock our throttle to 0.5, and then we'll again say until false. And now we're going to go ahead and say take the magnitude of this difference. Now, the magnitude is kind of the overall length of this vector. So as we null out our velocity, it should become smaller and smaller and smaller. So what we're going to do is we're going to do kind of the same trick that we did for awaiting closest approach. We're going to grab the magnitude, we're going to wait a second, and then we're going to say, okay, well, is the current one greater? Are we making the difference in our velocity worse? Well, if that's the case, then we're done. We've canceled out as much velocity as we can, and now we're firing and creating different velocity in a different direction. So turn the throttle off and go ahead and break out of this loop. And we'll talk a lot more about vectors in future episodes, but I don't want to get too far into it because we have Kerbals to save. Next, we have our approach function, and this is going to be a lot more simplistic, though we could make it more complicated if we wanted to. We're going to lock the steering to the target's current position, wait 5 seconds to let it finish its steering, and then we'll lock the throttle to 0.1 and let it burn for 5 seconds and then turn it off. So all we're going to say is point at the target and then go that way for a little bit. And that is all that we really need for our close approach adjustments. But the last thing that we need to write is this change period function. Now, I've written this out so that basically we accept a new period. So we're telling it this is the amount of time that it should take us to complete an orbit. We'll say, okay, we'll set our current period to whatever our ship's orbital period is. And we'll say set boost to new period is greater than current period. And this is going to be true or false based on whether or not we need to make our orbit larger or we need to make it smaller. If we need to boost our orbit, then we'll lock the steering to prograde, and otherwise we'll go ahead and lock the steering to retrograde, right? That makes sense. If we're trying to boost our orbit, you burn prograde. Great. So we'll wait 5 seconds, let it finish its steering, and then lock our throttle up to 0.5. And then if we are boosting our orbit, we'll wait until our current orbital period is greater than what was passed in as the argument. So if we said, boost it up until it's 100 seconds and we were at 50, well, then we would continue throttling until we're at, 100 and 101. If we were not boosting, if we were having to lower our orbit, then we would wait until our orbit was just a little bit less than what our target was. And then once that's done, we'll lock our throttle to 0. So these are all of the functions that we need to write our rendezvous script, and by kind of hiding them out in this individual file, it makes our rendezvous script itself much easier to read. And back to our ship, we have uploaded the new instructions, and it should be downloading. There we go. Beginning the rendezvous procedure, and we see it has targeted Sigkin's Hulk, and it is warping ahead until we get to the periapsis of our orbit. By the way, you can also say, set warp to and a value between, I think, 0 and 8. It is a part of KOS. I have been trying to avoid using it in actual scripts, but I've been sneaking it in every so often just to try and reduce the amount of actual footage that I have to record and then edit and speed up later. But there we go. We are now ready to boost our orbit to make sure that Sigkin's Hulk can... There we go. All right, back to the map view, and we see that we are boosting up the orbit, and Sigkin's Hulk is a significant amount behind us, which means that we're going to have to go up a fair amount. We're bringing that apoapsis up, and we see we are burning a not insignificant amount of fuel as we are doing that. But hopefully that by the time we're done with that, we can go ahead and let the other vessel go ahead and catch up with us, so that by the time we reach the periapsis again, these two things will be in approximately the same-ish position. Now, it's important to know that this is not the most efficient way to do a rendezvous, to delay our orbit by such a huge amount, because by the time we get back around, we're going to pretty much have to fire in reverse the same amount, which means that we are using the amount of fuel that we used pretty much twice just to delay our orbit, where if we were to try and spread that out over a longer period of time, we would be more successful. But we see the craft in the... to the lower right is slowly starting to catch up with us. It was kind of a third of an orbit behind, and now it's picking up. If we draw kind of imaginary lines from the center of the planet, and there we go. We are getting really, really close now, angle-wise, and hopefully by the time we reach that periapsis, we will be somewhat co-located. I'm just bringing up the nav balls so we can keep an eye on that. And yeah, using these warp scripts has been really helpful, at least in trying to keep the amount of video recording that I have to do down, though it still ends up being quite a fair bit. And there we go. We're just waiting until we hit our periapsis, at which point we will wait until we get to our closest approach, and then we will try and kill. Yep, okay, we're turning around and ready to kill our velocity, but you see that is 250-ish meters per second that we have to kill because we are so much faster than the other craft. And unfortunately, because, you know, we're only throttling at half, it is going to take us quite a while, and this is getting further and further away as we are trying to slow down. So we are going to have to do a lot of corrective maneuvers, but unfortunately, that will have to be in the next episode. So I will see you then. Cheers.